We are going to start the lecture on nanotechnology in chemical engineering. Today we will discuss about characterization techniques, FTR spectroscopy. So we have prepared various type of nanomaterials, carbon nanotubes, fullerenes, and then that materials we have functionalized with various functional groups. So sometimes this technique is very useful. So hence we need to know the what type of functional groups are present in that particular materials that we have prepared. So in that case today we will discuss about the spectroscopic techniques. So basics about what is called spectroscopy, so that we will discuss to get an idea about wave number. Means when we talk about FTR spectroscopy, sometimes we plot that spectra in terms of intensity, that is absorbance intensity with respect to the wave number. So what is wave numbers and how that is coming, so that things we will discuss about that basic description of spectroscopy. And then various mode of measurement of IR spectra, means when we have the samples, so various way you can measure the spectra, that will discuss for analysis purpose. So here the spectroscopy actually that is the study that interactions of electromagnetic waves with the materials. Suppose we have that materials or the molecules, once we have electromagnetic radiations or some energy that would fall about that materials, so there is some amount of the energy that would be absorbed by the materials. So then there will be some changes in that materials, so that may be in terms of structural, means vibrational change, rotational change, or electronic energy changes. Many way that may be changed depending upon that electromagnetic radiations that is interacted with the materials. So here the energy when it is, means few components we need to know about the quantizations of the energy, that is these energies of the molecules that are quantized, and a particular molecules can exist in different rotational and vibrational energy states or levels. So means considers two possible energy states of the molecules. Let us say ground state is E1 and excited state, that is E2. So whence the energy or electromagnetic radiations that is fall on the materials, that would be absorb the energy, then it would move from ground state to the excited state or higher energy state. So there is the amount of the energy that is being absorbed by the molecules, that we can express in terms of this, and that is the difference of energy or absorbed or emitted amount of energy by the molecules or the system. So here you can see, so this is the two energy levels, so levels 1 and this is level 2. So if we that amount of the energy being absorbed or that being emitted, so then it would, the molecules will move to the higher energy state, that may be in terms of rotational, vibrations, or electronic transitions. So here's corresponding frequency or wavelength that we can express that way. So the amount of wavelength or energy in terms of energy or frequency that is falling over there, so we can measure or we can calculate if we know the total amount of the energy, this transition energy, and if know the Planck's constant, so then frequency we can easily calculate. So, okay. So here means for this with that means the amount of the molecules get adjusts, means that may be in a systems we may take a small concentration or high concentrations of molecules, means concentrations means the number of molecules present in that particular systems. So all molecules will get absorbed. So depending upon that, so the amount or number of molecules that initially present at that particular state, that will be moved from lower to the higher states. So that actually expressed in terms of populations of that particular state. And another component is, that is the concentrations or path lengths of the samples. So that means actually amount of the materials that is present, or that is molecules, the amount, the energy, that is delta E, that is the amount of energy that is being absorbed for that particular spectrums that we are getting from that sample. So that actually increase, that actually indicated actually. So let's say total in number of molecules that is being distributed from that lower to the higher energy states or two different states, so that we can express a number of molecules that is present in lower, a number of molecules present in the upper energy states. So then that we can express in terms of the amount of energy changes, K constant, that is a Boltzmann constant, and this is the temperature within that the molecules is moving from lower to the higher transition states by absorbing the electromagnetic radiations. So here also the concentrations, path lengths, incident and transmitted radiations. Here's Beer-Lambert law is there. Here's this actually also I by I0, that is the I0, that is the incident radiations, and I is the transmitted radiation that is passing from that molecules, means through that molecules that is passing. And here's gauge constant for spectroscopy. See, the concentration cell is the path length. So within that, the means depending upon the concentrations, the molecules also get absorbed depending upon the path length also. Okay, so here's, let's say, lower state, that amount of the molecule is present. So if the amount of energy that is being absorbed, so then it would move to the upper state. So here we can measure the populations, means how much molecules or amount of the energy being absorbed, and based on that how much molecules being reached to the upper state. So here's using these correlations. So here's, if we know delta E, that is h nu or hc by lambda. So here lambda is the wavelength of that radiations that is being fall on that samples. If we know k, that Boltzmann constant we know, see that is the velocity of the light is known, so h Planck constant is known. So this the amount, means from the wavelengths we can get that energy, and then that we can put it here, Planck's constant we can put, and if we measure that at, let's say, 300 Kelvin temperature, that experiment is going on. So then in upper to in lower, that we can get 0.98 for example. So from here we can say that the amount or this amount of wavelength that is being, or energy that is being fall on that molecules. So 98% of the molecules moves to the lower energy state to the higher energy state. So that actually means this way we can express that. Also there is a characterizations of the electromagnetic radiation. So in terms of simple harmonic waves or sine wave, we can express y equal to a sin theta. So here's details, I am not going to discuss this. Electromagnetic wave or electromagnetic radiations, and that is as a simple harmonic waves propagated from one source and traveling a straight lines that expressed in this way. So here's in terms of angles or theta, it is expressed the wave, that is sine wave that is propagated, that can be expressed in terms of wave number also. So here if we change that in terms of wavelength and wave number or velocity of light, so these equations we can express in terms of y a sin 2 pi nu x. So x is the distance that is covered in time t at the speed of light, that is c. Okay, and nu bar, that is wave numbers. So that is 1 by lambda equals to nu by c, or it is expressed in terms of centimeter inverse. So that way means we can express the distance travelled with the speed of light, that electromagnetic radiations. So simple harmonic wave of sine waves, that we can express this way. So here the electromagnetic radiations, what is electromagnetic radiations? So here's electric field and magnetic fields when they are interact, and so then in radiation that consists actually discrete packet of energy which called actually photons. So here's electric fields and magnetic fields and electric fields, that actually consist actually two different oscillating electric fields and oscillating magnetic fields are perpendicular to the each other. So that is the actually electromagnetic radiations that we have shown. So here's actually when that interact with the molecules, so different way it may be absorbs that energy, reflections, transmissions, scattering or reflections. Many way means, let's say this is our molecules, when light is passing, light in the form of energy or electromagnetic radiations you can see. So that energy may be absorbed, some in that molecules, some will be transmitted through, or some will be reflected, some will be scattered, and some will be refractions. So depending upon a particular analysis, so a particular means mode of energy we can, means either transmission mode, absorption mode or reflections mode we can collect with the help of the detectors, and we can analyze depending upon our application. So here electromagnetic spectrums, there are energy range, low energy to the high energy. So these are the basic things. So here's means wave length that we can say, that is the in that range. So when it is radio wave, so that is in that range, so that can be used for NMR or ESR spectroscopy. when it is microwave range, that can be used for rotational spectroscopy, and when it is infrared, so vibrational spectroscopy, so that actually used in FTIR. So that is why I am saying, so here mid IR, so it also can be means splitted up into three different range: mid IR, far or near IR. So mid IR, that is used for FTIR spectroscopy, and apart from that there is visible range, ultraviolet range, so that also can be used for UV spectroscopy, and X-ray, that is for X-ray diffractions analysis, that can be used. And this just to get an idea about the electromagnetic radiations ranges and that particular ranges that are being used for FTIR spectroscopy. Okay, so here's different electronic energy level, vibrational energy levels, and rotational energy levels, so that have been shown, and each different energy levels having energy that is different. So electronics energy, that is much more greater than vibrational energy, and then rotational energy. So when molecules absorbs UV lights from the electromagnetic radiations, so then there is a transitions of the electrons, lone pair electrons or bonded electrons from that molecules, that would be promoted to the higher energy states. So then that is the electronic transitions here. From this is, we can see ground state, and this is excited state. So here's electronic transitions may be there, or maybe when it is vibrationals, so electromagnetic radiations in vibrations range, so that is being absorbed. So then there is changes, the vibrational changes in that molecules. So then the molecules also means IR radiation, for example. So if IR radiations from electromagnetic radiation that is being absorbed molecules, then molecules will be excited from one vibrational levels to the another vibrational levels, or here you can see from this ground state to the these vibrational energy levels, that is lower than electronic energy levels. And then rotational energy levels also, when molecules being absorbs rotational energy, means energy absorbed, so the amount of energy, and there is changes in rotational movements of that molecules, then the rotational level changes, that is the energy difference, that is very small. Okay, so here means the from the electromagnetic radiations, I said in this range, so infrared range, so that is being used for vibration spectroscopy in FTIR. So mid IR, that is being used. So here the FTIR spectroscopy, it looks like this. So here's actually when molecules having some dipole moment change in that molecules, so then with the help of IR spectroscopy we can get the vibrational change in that molecules, that we can collect, or that kind of informations we can get with the help of FTIR spectroscopy. So I said the IR range, that is far, mids and near IR range. So here's in FTIR spectroscopy, that is huge mid IR range, that is 400 to 4000 centimeter inverse, within that range. So here just in terms of wave numbers or wavelengths, so that is being used, means wavelengths 2.5 to 25 micrometers that we can use, and wave numbers 400 to 4000 within that range. So interconversions can be done. Okay, so here means when IR mid IR, that is fall in any molecule, so there may be changes in molecules when molecules get absorbed by that particular range. So in normals, let's say one car CO2 molecules was taken, so when there is maybe stretching or maybe compression, this kind of changes may be there in that particular molecules. So here the stretchings may be symmetrical stretching or asymmetric stretching or antisymmetric stretching. So symmetric stretching, that is not, since dipole moments would be 0, as a result it would be IR inactive. When asymmetric stretchings would be developed in that particular molecules, so then there would be change in dipole moments and that molecules will be IR actives. So then that particular IR active band or vibrations that we can see with the help of spectroscopy spectrum, so or IR spectra. So with that we can say, or we can identify that particular specific bonds or functional groups are present in that particular molecule. So here's asymmetric stretching vibrations of CO2 molecules and bending motions, that is changes in that molecules when IR fall on that molecule, CO2 molecules. So these type of changes might be there, and there is a changes in dipole moment. So how dipole moment changes is there, so when there is a asymmetric stretching, and dipole moment change when bendings is there in that molecules, the changes. So this is changes, you can see that is the changes of bending vibrations, and this is asymmetric stretching. You can see this is means in that molecules that carbon oxygen's bond is present, CO bond is there, is the if it is stretching then asymmetric way of stretching, so then this type of dipole moment may be changes, and that may be we can with the help of IR signals. Okay, so in there is the basic component present in IR spectroscopy or a spectrometer. So here is the source, IR source is present, interferometers is present, and then sample compartment detector and computers of course would be present. So here source, that is the IR source that would come to the here beam splitter is present, and see here's one moving mirrors, another stationary mirror that are present in inside of that equipments and FTR spectrometer. So here's the sample compartment is there, and after that what are the light will pass through the samples that come to the detectors, and with the help of amplifier or computers we can get that FTR spectra. Okay, so here's means how things are going on, means this is the incident lights I0 when in molecules a particular concentrations we have taken that being absorbs the IRs, and then the rest will be leaving or transmit from that samples. So through that instrument, so the amount of the intensity we can find out or we can measure. Okay, so this is the Beer-Lambert's law. So depending upon the concentrations, the absorbance is the absorbance, and here C is the concentration. So that is the molecules present in that particular samples that we can analyze. Okay, here's the basic difference between normal IR and FTIR. So initially at that beginning, so there was IR spectroscopy, later that is converted into FTIR. So in IR, that disadvantage is conventional, that is methods producing the spectrum that is inherent slowness, and in FTIR that we get instantly, means we can get simultaneously whole spectrums we can record throughout range 400 to 4000, that spectral range simultaneously we can record, that is the advantage. So that is the very fast compared to the conventional IR spectra. Okay, so here actually in Fourier transform the time domains that converted into frequency domains, as a result throughout the range we can get added times. Okay, so here's few theories are there, so I am not going to discuss. So here's I said in that molecules, so when IR's energy that would be fall on that sample, so then there would be changes in dipole moment in that molecules. So when there is a dipole moment change in the molecules, so here in IRs within range 400 to 4000 meter IR, so the vibrational frequency of specific bond functional groups that we will get, that is we can express in terms of nu1, nu2, nu3. So that is called actually fundamentals bands. Okay, so in fundamentals bands, and then we can get overtone bands also, that overtones bands that is multiplied with 2, 3 like that with the fundamentals bands. So if fundamentals bands is new ones, then overtone bands we can get 2 new ones, that is the first overtones. If it is multiplied with 3, then we can get second overtones bands. Also we can get combinations bands also, nu1 plus nu2, if vibrational frequency is nu1, nu2. So both may be sum of sometimes this way, we can get combinations bands, that is actually usually comes in near IR. And difference bands also sometimes we can get if nu1 is having higher frequency and nu2 is lower frequency, the difference bands also sometimes we gets with the help of spectroscopy. Okay, see here's the mode of vibrations I said. So in some molecules there may be some functional groups are present, so there is a dipole moment change. So here's let's say CH, two different atoms are present. So here's there is in terms of stretchings or in terms of bendings we can get two different mode of vibrations. So here's if it is stretching, so asymmetric stretching or symmetric stretching so we can get, but symmetric stretching it's very weak in case of IR. Asymmetric stretching should be much more stronger, so that's bands of CH bond vibrations we can get. And also the bendings you can see the CH bond bends, position changes. So that also we can get with the help of this IR spectroscopy. Okay, so here's the frequency, means stretching frequency, how we can calculate, means at what particular range. So let's say we have CH, this particular bond is there, so at what particular locations the stretching frequency would comes of this particular bond. So here the for dieting molecules, so absorption frequency for the stretching, so that can be expressed in this way, nu equals to 1 by 2 pi c square root of k by mu. Here mu we can express in this way or this way, where m1 m2 that is the mass of atoms, this is carbon atoms and hydrogen atoms, that mass we can get in terms of grams, or capital M1 M2 in terms of AMU. So we can get, once it is in terms of grams we can use these expressions, and when it is in terms of AMU we can express in this way, and then we can put the, means this mu whatever that would come, that we can put here. Here small k, that is called force constants, that we can use. So here let's say, means different type of bonds may be there, that functional groups, that may be single bond, double bond or triple bonds. So if it is single bond, k would be, you have to use, that is the force constant, or 5 into 10 to the 5 dynes per centimeter. So if it is double bonds, if it is triple bonds, we can use that type of value in here. And then if you know the velocity of light in terms of centimeter per seconds, that we can put. So then by stretching frequency, that we can calculate. See here 3 examples are showing. Let's say CH bonds, CC bonds, CO bonds is present. So what would be the stretching frequency? Here this bond is single bond, here this bond is double bond, here this bond is also single bond. So depending upon that force constant, so that would be used this. Okay, so here you can see CH bonds, bond vibrations or stretching frequency, that would come here in case of CH bonds. Similarly for CC bonds, so within that range we can get the stretching frequency. When CO bond, single bond is there, so we can get C double bond O also we can get. So then accordingly for this k value would be changed and frequency range would comes different, okay, at different locations. Here different functional groups are showing, and the stretching frequency depending upon that particular bonds and the compound, so it would be different. So depending upon the molecule structures and environments, so that functional group stretching frequency would vary. Okay, so here various modes of IR spectra that we can get, means we can measure the spectra or analyze, then analyze the sample spectra. So once we have prepared that maybe materials or compounds, that is let's say nanomaterials we have prepared, that is present in solutions, so liquid phase, or maybe in solid materials we have prepared thin films we have formed, so or nanoparticles that is forms in layers, so that we can get the spectra or we can check with the help of IR spectra. So different way or mode we can do the analysis. So here suppose we have a liquid sample, so in transmission cells is there, it is called cuvette, so there we can put that samples, or means zinc selenide window is there, so within that cell, means this type of cylindrical flat cell is there, this is made of ZNS. So in between two ZNS window, so there we can place that liquid samples, and then IR may pass through transmissions modes, and then we can get that spectra. Or so we can make KBR pellets if the materials is, let's say, solid powder, so we can mix with KBR powder, and pellets we can make very thin pellets, and that we can placed in between IR source and detectors, and then we can get the IR spectra. Okay, IR spectra we can get. Similarly in ATR mode also we can measure the IR spectra by using zinc selenide crystals I said. So this is IRs will pass from source to detectors, and here we can place our samples, so we can get easily in ATR modes the IR spectra we can get. And another one is DRS mode also, diffuse reflected light, that may be collected, or diffuse reflected spectra we can say. So here solid powders we can place in a sample holders, and then IR will pass in, that would be collected, different mirrors are present, so at different angles. So what would be the diffuse reflected spectra, that would be collected and come to the detectors from that source, and with the help of that diffuse reflectance accessories we can get the diffuse reflectance spectra. Okay. Similarly, specular spectra also we can get from that surface that would be reflected directly. Okay, so here's the details is given, so we can study or read that. So in case of the polyatomic molecules, also number of vibrations or degree of freedoms, that is for non-linear molecules, linear molecules. So fundamentals bond vibrations, that would be for non-linear molecules, and this is also for linear molecules. So that is being showing here. So here's this is waters on CO2 molecules, different mode of vibrations might be present. So here symmetric stretching, this is symmetric bendings, this is asymmetric stretchings. So nu1, nu2, nu3, you can say the stretchings produce no changes in dipole moment, so that is not IR active. So mostly whatever the asymmetric stretching or antisymmetric stretching, that we can get strong signals with the help of FTR spectroscopy. So usually in case of the water, that is come usually 3755 centimeter inverse within that, so that strong signals we can get. Okay. And in case of the CO2 molecules, four mode of vibrations is there. In case of the water, three mode of vibrations since it is and not linear molecules, this is linear molecules. So this is not linears, this is linear molecules. So in that case, three different four mode of vibrations we can get. So here's the bendings, maybe one is in planes, one is out of planes. So this asymmetric stretchings, whatever that is coming 2349 centimeter inverse within that, that would be much more strong signals we can get. At the same time, bendings also we can get in the FTR spectra. So in FTR spectra, when we do the sample analysis, so then initially we have to put the samples, and then we have to measure the background spectra or background, this is background signal. So background spectra we can get like this, and then once background background spectra we get, after that we place the samples and we get the sample spectra. So this is be the sample spectra. Here x axis we are placing wave number centimeter inverse, and y axis that is in terms of absorbance or in terms of transmittance also we can express. Okay, so here's few examples of means with alumina that was taken as a powder samples, and over there different hydrocarbons was mixed up, and then DR spectra was taken. So x axis wave numbers, y axis that is the concentration on absorbance is showing. So in case of the cyclohexanes, so this is the CH bond vibrations we are getting, only cyclohexanes in molecules. You can see all CH bond vibrations, CH bonds are present, so only that we can get. So that is coming usually within that range, CH bond vibrations. So within 3000 centimeter inverse within that range. So in case of the CO2, you can see 2, 3, 4, 5 usually comes, so within that range. And different hydrocarbons, methane, ethane, propanes also we can see here, ethanes or propanes. So whatever that is coming, so within that CH bond vibrations is coming. So one compound to another compound, so structures are different, so but the functional group that is present, that is CH, so usually comes within that range. Okay. So thank you. So today is up to this. So we have studied so IR spectroscopy and how IR spectroscopy or IRs, that is FTR spectroscopy, can be used to characterize different functional groups that is present in any molecules or hydrocarbons or any nanomaterials that is we are going to study. Means once we study that material, so then suppose T or fullerenes, various hydrocarbons, various carbon nanomaterials we have prepared, and then we have changes its property by functionalization. So whether there is functional groups present or not, we can check that with the help of this spectroscopy. So this FTR spectroscopy is useful for this particular study to get the vibrational spectra of that molecules, if there is any functional groups is present and that is IR active, that we can easily detect. Okay, so thank you. So today is up to this.